part of intermolecular forces is sort of like how we did periodicity, where once you learn the general trend, everything else relates back to it. So if we knew atomic radii, we could relate ionization energy and all that. So you already learned in lecture 1 of this who's the strongest type of intermolecular force, right? So if we know the strongest intermolecular forces, then we can rank our heat of fusions, our heat of vaporizations, and then vapor pressure. We'll just probably get through these 3 today, and then we'll finish the other 2 tomorrow. Not so many problems for this, so we might get some of them done in class too today. All right. Chemical versus physical. This is what we just discussed a moment ago about breaking bonds versus severing intermolecular forces. So chemical processes involve breaking and forming new things. So I take a certain compound and I can break those bonds to make something else and react them with something else. So you have to form new substances. Whereas a physical process is just intermolecular forces, you're usually doing a state change. There's this random gray area. So it's truly like some people will debate it and they don't agree with each other about whether or not dissolving salts is a chemical or physical process. So if this question is posed to you, they give you one side of the argument and they just tell you to justify it. That's usually how they present it. They don't ask you to like pick a side. So I have seen this happen before on an AP exam. They'll tell you a statement and then you have to justify it. So why would dissolving salt in water be considered a chemical change? Anybody know? So chemical changes are what? Breaking. So what would you be breaking? Salt. So what's salt? What kind of attractive force is that? So ion, right? That's what I'm looking for. So think of all of your rankings. Ion, dipole, 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 which hydrogen bonds are above that. Think of that list. So if you have salt, you're breaking the ion forces of attraction. And what are you forming with water? Ion dipole. So in a sense, it's a chemical process because you're breaking ionic bonds, and you're forming ion dipole. But in the same sense, I could just evaporate my ion dipoles, the water, and I would still be left with an ionic compound. So you're not technically forming anything new. So some people will argue, well, then that's not a chemical change, it's just a physical change. Plus, there's some heat involved in that ion breaking and the ion dipole forming. You actually get a change in temperature for that process. So this could be chemical, and if you want to justify that it's chemical, then you talk about the breaking and forming of bonds. And if you want to justify that it's physical, then you just talk about intermolecular forces and the fact that you can get salt back after it evaporates.
What do you think it is?
I don't really care. What do you think it is?
Chemical.
Chemical. Physical. Okay. This is a great diagram. So you're definitely going to see this on my exam, and you're definitely going to see this on the AP exam. And the best way to approach it before you even look at any questions is to label it. So this is what you should do every time you get one of these, is you label it to start. This is solid. It doesn't say it for you, but obviously the coldest one on a temperature going up, the coldest part will be solid. So you go solid to solid. When it's flat is when it changes its state, solid to liquid. And then when it goes back up, it's liquid to liquid. And then flat again goes liquid to gas. And then up again goes gas to gas. So you're going to be solid, 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 liquid, 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 gas, gas, gas. And once you've labeled it, it should be pretty simple for you to answer any of the questions about it. If you don't label it, you're going to mess it up. So heat is being supplied. So think of water, ice. We start out with a solid. We're heating it up. And it begins to go, the intermolecular forces are tight, and then the kinetic energy of those particles begins to increase. So in case you don't remember, or you don't know, temperature is directly related to kinetic energy. So if temp increases, kinetic energy increases, and vice versa. So kinetic energy is literally the movement of those molecules. So if I start heating up those molecules, they're going to start moving faster and faster, and they're starting to weaken their intermolecular forces, right? They're moving faster and faster. So from this point to this point, If you have ice and you start heating it up, the temperature of that is going to increase. But it's still solid. You don't actually see any liquid water droplets yet. And then as soon as it begins to melt, which is called heat of fusion, delta H is enthalpy. So delta H stands for enthalpy. Yeah? Thank you. Oh boy. All right, let's pause this. So delta H is enthalpy, and this just means heat, typically, like energy in the form of heat. So if you're supplying energy to the system, the temperature is increasing, kinetic energy is increasing, and then you get to this spot. So literally while it's melting, that ice is now partially solid, partially liquid. Like you can envision this, right? You can see that it's halfway there, and then at some point it gets all the way to liquid. At this point, you do not see any temperature change. In fact, the temperature will not change at all until all of it becomes a liquid. So now all of the energy that's being supplied in here is no longer increasing the kinetic energy. It's all being used to weaken the intermolecular forces. So jot this down. Energy added at this point is used to weaken intermolecular forces to change the state from solid to liquid. Whereas this point, energy is being used to increase the kinetic energy and then therefore increase the temperature. All right, so then we go up the curve again. So now all of our ices become liquid, and now we begin heating the liquid again. So again, same thing, energy is being used at this point to increase the kinetic energy of the particles. As kinetic energy increases, the temperature increases. And then we get to the boiling point, which is called delta H of vaporization. So that one's easy to remember because vaporization clearly means you go into the gas phase, whereas fusion is sometimes hard to remember that that's the solid to the liquid. But your liquid to the gas is the delta H of vaporization. So heat's absorbed here to increase kinetic energy. At this point, your heat that's being absorbed is only used to do what?
Change the liquid to gas.
Which energy added is used to break or sever. So now the energy here is used to sever intermolecular forces to go from liquid to gas. And then you can continue heating it, and the gas particles can be heated because they can move faster and faster. Their kinetic energy is increasing. And so you would just increase the temperature of that gas system. So the most important thing to note is that when you are in the midst of a change of state, that you do not see a temperature change. If you boil water, pure water at home, it should boil at 100 degrees C. Let's just be clear that you know that water boils at 100 degrees C. It also liquefies or solidifies at 0 degrees C. And so if you're boiling a pot of pure water at 100 degrees Celsius, all of the water will stay at 100 degrees Celsius. You put your thermometer in there, you're not going to see it go 100, 101, 102, 103. It does not increase in temperature. And that might be new for you. Like maybe you just assumed that it did that because you've never learned this before. But the temperature stays exactly at 100, and it's not going to change because what's going to happen to your pot of water? It's going to eventually all boil off, and you will have no water left in there. Have you ever done that? Just forgot a pot of boiling water on the stove, and now you're just heating up metal. So the temperature of that water is 100 degrees, and then it goes away. And the temperature doesn't change, unless, of course, you're measuring the temperature of the pan at that point, or the pot. And then you can increase the temperature of the gas. But water boils at 100 degrees Celsius and stops. It never increases. Any questions on this? Yep.
As far as like the heat at the bottom, that just means that the heat of the
Me adding heat. Not the heat of the substance. Like I'm supplying the energy in order for this to happen. So you could literally think of it like a flame underneath. So the heat that's being added is either increasing kinetic energy or it's weakening or severing intermolecular forces. And when you weaken or sever, temperature won't increase. Make sense? Okay. This is a cooling curve. How do I know it's cooling and not heating? It's going down. And look at where you are on your graph. Your temperature is up here, so you're starting high and you're going low, right? So this is a cooling curve. Same thing, always label it. So when you see only one piece of a graph, like even this piece, if they don't tell you what you're starting with, you don't know if this is going from a solid to a liquid or a liquid to a gas. You'd have to be careful to read what the question says, but sometimes they only show you one piece of the graph. So this time they're only showing you one piece of this graph. You can know typically that if they just show you this, that this is a liquid to a solid one, because this is called a supercooled curve. And the way you know it's a supercooled curve is because you have this little hump here. So what this really should look like, if it's not supercooled, is a straight line. And if we labeled this, this would be going from liquid to liquid, liquid to solid, solid to solid, right? Always label them. The flat parts are where you're going from your change of state. So as heat is being removed from the system, we go down to this little spot here. So we're cooling our liquid, and then we get to this little hump. And what this hump is a supercooled liquid, which means that you've gone below the freezing point of that liquid, and it's still maintained a liquid state of matter. It's not a solid at this point. So this is, say, for water, we're at 0 degrees Celsius, but I've actually gone cooler than 0 degrees Celsius, and I'm still in a liquid. So some of you may have experienced this. You can, even if you've watched YouTube videos or something, you might be able to think of an example of this. Does anybody know? Rob?
Like when you leave water in a garage that's like super cold and it stays still, but then you pick it up and like hit it, it changes.
Have you done this or only watched a video of it?
I've done it once, but it was like 6 years ago.
This happens a lot. And as you guys start driving, there's a good chance that you're going to have water bottles in your car. This happens all the time in my family because we always have water bottles floating around in the car. And it needs to be fairly pure water for this to happen, but you're drinking that in your water bottle anyway. And it's winter and it's cold and you get a bottle of water and it's still freezing cold outside. It's like 20 degrees. And you have liquid water still in this bottle. And then you go to crack it open, and just that movement jostles it enough that a single ice crystal might form. And at that point, the rest of the entire bottle will start to solidify. So you might start drinking it, and all of a sudden more and more ice starts forming in your bottle, and then all of a sudden there's no water, liquid water left. Does that happen to anybody? You ever tried that? Yeah, it happens all the time in my husband's car because he always has these water bottles and he's drinking them. The other thing that you might see on a YouTube video is that they do set it and then they smack it really hard, and that smacking process usually solidifies the whole thing all at once. There's other experiments called hot ice, not entirely exactly the same as this, but where you can like pour a liquid out and you almost see it solidifying into a cone. That has something to do with this too. So we see this temperature drop lower than it should, but then we see a spike, which means that temperature went up. So it's super cold, and then all of a sudden we see an increase in temperature. So you need to understand why that increase in temperature occurs. So we're down here at a liquid, still at a liquid, and then we spike to a solid. So when you have a liquid going to a solid, are you breaking or forming bonds? In a sense, we are, right? Even though they're not bonds, but they're intermolecular forces, we're strengthening them at that point. And so when you go to a liquid to a solid, this is an exothermic process, which means that it's releasing heat. And so at that point, when your supercooled liquid all of a sudden becomes a solid, it releases heat and you see the temperature of the system rise, just for that brief moment. So as a side note, I'm going to write this stuff down again. This is a little bit thermodynamics, but endothermic processes are always positive values, and they're always involved in bond breaking. Exothermic are negative values, and they're always involved in bond forming. So this is absorbing heat, and this is releasing heat. All right, so that should make sense to you. As your super cooled liquid goes down, temperature is lower than it should be, and then as soon as it goes to make a solid, you release heat because you're forming bonds. So when bonds form, it's exothermic, heat's released, and you see a quick jump, which means now that all of this liquid is now turning into a solid. So that's why it flatlines. Kinetic energy is not increasing, so temperature is not increasing, and all of the energy at this point is being used, since I'm going from a liquid to a solid, to solidify those intermolecular forces, right? We're not weakening them because we're trying to strengthen them. So you can use the word strengthen or solidify the intermolecular forces. And then we can cool it even further below its freezing point. So freezing point, melting points, same temperature, right? It's just that flat line. It just depends on the process that you're at. As a side note to this, it's not part of the curriculum anymore, but it's still interesting chemistry. It's called Colligative Properties, and they've removed it from the curriculum. But you know that this kind of stuff happens a little bit in terms of when it's cold out and there's ice. What do you guys put on the ice? Salt. So colligative properties basically mean that when you mix compounds with water or any other kind of solvent, you change the melting points, the boiling points, freezing points, you change them by adding something into the system. And so it's sort of like this, a little bit different, but when you put salt on your ice outside, which is water, you actually depress the freezing point, which is called freezing point depression. And so the higher the concentration is of the amount of the salt that you put on or put it in the water, the lower the freezing point temperature will be. Also, the more ions that you have, the lower the freezing point will be. So when you throw salt out there, you're basically trying to lower the temperature of the freezing point of water so that it's not going to freeze when it's cold outside. You're trying to lower it so much. Part of the problem is you need a lot of salt to do that in order to lower the temperature of the water significantly. So most of the time, those bags of salt that you have aren't actually sodium chloride. Does anybody know what they might be? Calcium chloride or other salts that have more ions. How does calcium chloride have more ions than sodium chloride? What's the formula for calcium chloride? CaCl2. So when that dissociates into water and breaks apart, you have 3 ions versus NaCl, which only has 2 ions. So the more ions and the more salt you have, depending on what salt you put in there, would lower the freezing point of water even more. And the other thing is true, I don't know if anybody, when you put salt in your water at home to boil your spaghetti, it's really just for flavor, because some people used to say that it'll help cook the spaghetti faster. Does anybody's family ever say that? Yeah, that's like nearly impossible to do, and you can explain to your families how. You would have to put so much salt in your water to increase the boiling point. So colligative properties work that way, where if you've added something into that water, it will adjust the freezing point and the boiling point. So the idea would be it's going to cook my food faster because I'm going to increase the temperature at which the water boils. So if the water is supposed to boil at 100 degrees C and now I get it to boil at 110, I can cook my food faster. You would have to dump in like an entire bag of salt for that to happen. So it technically is just flavoring your food, and it's not actually going to increase it substantially enough. But when you're outside and you throw an entire bag of salt onto your driveway, there's probably enough ions and so forth to get it to lower the freezing point. Not related, but just interesting chemistry so that you know these things when you're doing them. All right. Solids. This is just a picture to show you what happens when you are weakening intermolecular forces. So how do I know that this is a solid? I mean, not a solid. How do I know that these are molecules? So these are where you look at particulate diagrams and you have to be able to recognize what it is. Why is this not an ionic compound? Ionic compounds are circles, right? What would what? They have some sort of attractive forces next to them like that, but what's another clue?
Don't ionic bonds like directly connect.
So if this were ionic, I would have one circle for each cation and anion, and they would be sticking together, right? And should there be pluses and minuses inside those circles?
No.
Not together, they would be separated with one plus and one minus, and then they would be connected or touching each other. So I know that this must be a molecule because of the way it's drawn. What kind of intermolecular forces are present here? From the drawing. Dipole, dipole. How do you know? Because one end is positive and one end is negative, which creates a dipole. So just when you look at it, you should be able to recognize this is a molecule with dipole-dipole forces of attraction. And so this is just showing you that they're held close together, and then when we weaken them, they begin to move around, and we're releasing or moving them so that these intermolecular forces are stretching or weakening. I use the word weakening a lot, but stretching is another good word. Don't use severing. So heat of fusion, delta H of fusion, is the heat absorbed as 1 mole of a solid liquid phase. So we'll get to thermodynamics a little bit later, but 1 mole of any substance is the delta H of fusion. Energy is required to expand, and don't use the word sever. Weaken the intermolecular forces of attraction as a molecule moves from the solid to the liquid phase. This is why molar heats of fusion values are always positive. Melting is always endothermic. I wrote that up here for you already. In order for this to even weaken, it has to absorb energy, therefore it's an endothermic process. The reverse of this is exothermic, but equal to the amount of energy that it would take to weaken them, right? Equal but opposite. If I'm melting or if I'm solidifying, same amount of energy is going to be released or absorbed. All right, how do I know this is ionic now? Can you see the difference? Pluses and minuses, and they're stuck together. There are no dot, dot, dots in between them because they're not intermolecular forces. They're stuck together by their attractive positive cations and negative anions. So the delta H values for this is much higher for that melting process. And that's because ionic bonds are much stronger, right? Ionics way above your covalent bonds. And then above that would be those covalent network solids that we'll talk about tomorrow. In liquids, we have very stretched out, weakened intermolecular forces. They're strong. They're the same forces that existed when they were solid, but now they're just stretched further out. And then in order for them to break, here is the delta H of vaporization. So at that point, we're severing those bonds, or those intermolecular forces. So this is delta H of vaporization is the heat absorbed as 1 mole of liquid becomes gas. Energy is required to sever the intermolecular forces. So again, this is endothermic, which means that you'll have positive values. And there's no, ideally, in the gas phase, intermolecular forces of attraction. So that's part of the ideal gas law, is that they don't interact with each other in the gas phase, although that's not true, because otherwise we would never get liquids to come back. So at this point, I want to discuss, like, you get this, but I don't know that you really understand how this works in your life. So 2 examples. When you sweat, you are causing all of this heat of vaporization to occur on your body. So your body starts sweating, you're hot, and on your face is water, but it's not water. What is it really with it? It's salt, right? There's salt in there. So what kind of attractive forces are there on your face? Salt and water is what? Ion dipole. All right, so you got ion dipole all over your face. Now you know that if you just stand outside for a long enough time, eventually you're not sopping wet with sweat anymore, right? You kind of like dry off, because what's the sweat trying to do? It's trying to evaporate. There's a delta H of vaporization for your sweat, right? So it's evaporating off of your forehead, off of your back, wherever your sweat is. And how does it use energy to evaporate? From where? From your body, from inside your body.
Oh, it takes your
Because you have temperature. The temperature of your body is high, right? If your temperature goes too high, you die. So how do we keep our internal temperature okay? We sweat. And when we sweat, we use the energy inside our body to vaporize your ion dipole on your face and all over. So that is why when you sweat, you cool off. It cools your body down because it sucks that energy out of your body to evaporate your ion dipole forces. Yes? So I don't know that that's like something you're supposed to do. But yeah, when you have a fever, you need to cool your internal temperature, which is probably why you might be sweating. But I feel like when you have a fever, you definitely, like, you can't really lower that temperature too much unless you put cold water. In fact, if you have a fever, the best way to lower your temperature is to get really cold towels and stick them under your armpits, not like your forehead, because that's closest to the internal temperature. So you just literally stick them under there. Yes. One more example would be when you're swimming. So it's 100 degrees outside, you jump in your pool, you feel great, you come out, it's still 100 degrees out, but what are you looking for? A towel. He didn't say that, I said that. A towel. Because you're cold, right? But why would you possibly be cold? So think about what I just told you. When you're sweating, what happens? What happens when you jump out of the pool? What's all over your body? Water. So just hydrogen bonds, dipole, dipole, right? All over you. And it's trying to evaporate and go into the vapor phase, right? It's doing that by sucking your energy out of your body and using it to evaporate all those water molecules. And now you're cold, but it's 100 degrees out.
I'm so confused.
Child.
Howard, she's talking about, like, she's relating sweat to, like, being cold. And I'm like, wait, but I'm hot when I'm sweating.
You are hot when you're sweating, which is why your body sweats to keep your internal temperature down. Okay. You are going to be hot.
So then why am I cold?
But you won't overheat. Like, you know that people overheat, right? And then they pass out because they overheat. If you overheat, you're not lowering your temperature enough. That you're just still using too much energy. Yes?
This is kind of like a dumb question, but...
Moving along. Vapor pressure. Here we are, Chloe. Next lecture, next slide. So vapor pressure sometimes can be confusing. And so I'm just going to draw you a picture before we even talk about any of it. Vapor pressure, you need to think vapor pressure evaporation. If I say vapor pressure, you think evaporation. And so if I have a closed system, and I have some sort of molecule down here and another molecule down here, and this one exerts a certain vapor pressure, and this one exerts vapor pressure. So this is low vapor pressure, this is high vapor pressure. So what does vapor pressure actually mean then? Like the concentration of particles in an area, right? So if this molecule can exert high vapor pressure, it means that a lot of it evaporates, doesn't it? And if this has low vapor pressure, there's not that many molecules of it in the gas phase, so this doesn't evaporate very well. Which one has the weaker intermolecular forces? The second one has weak intermolecular forces. So think about that. Weak intermolecular forces mean that it can't stay like this. It immediately is going off into the vapor phase. But if you have strong intermolecular forces that are holding tight, not many of them are going to be able to go into the vapor phase and evaporate. So this is strong intermolecular forces. That should make sense, right? If it's held tightly, you're not going to get that many particles that go off into the vapor phase. Think of a puddle of water, and then I have crystals of sodium chloride. Obviously not drawn very well. Which one evaporates at room temperature? We know water eventually will evaporate, right? Whereas an ionic compound, you don't see salt evaporating off of your counter, correct? That doesn't happen. So think of intermolecular forces. Really strong intermolecular forces have very low vapor pressure. Sodium chloride does have a vapor pressure, but it's very, very low, and so we don't actually see that evaporation process occur. But water we can certainly see. All right, so let's read the slide. Vapor pressure is when molecules leave the surface of a liquid to enter the gas phase. They exert a certain amount of pressure. How many of you have had surgery and can tell me when it's going to rain? Anybody in here? Can you actually feel that? Or is that just something that like old ladies say? It hurts. So what do you think's happening?
The pressure change.
The pressure in the atmosphere, when it's like gonna rain, means that there's a lot of water molecules in the atmosphere, right? Like so many water molecules that it gets too heavy in the cloud, and then the cloud releases rain, right? So that's vapor pressure. So Kristen feels it because it's pushing on all of her joints, and she can feel there's a lot of molecules in the air. Yeah?
Is that why you get headaches when it rains?
I don't.
I don't
Do
know.
you?
Every time it rains, I get a bad headache.
There's lots of environmental factors that could cause health issues. So, I mean, think of sinus pressure. So you guys, with sinus pressure and the change in weather, it certainly could make your sinuses and give you a headache, is that you can feel, you don't actually feel it, but the pressure of the atmosphere is being exerted on your body right now. So if there's a lot of pressure in the atmosphere, you would feel it. Think about it in terms of swimming. If you go swimming and you just go to the deep end, forget about going deep in the ocean, you go into the deep end, you can physically feel the pressure of the water surrounding you, right? Just like you're outside, there's pressure being exerted on you, but most of us can't feel it except typically people who've had surgery and they have injuries that they can feel the pressure, or like Kirsten who gets headaches because there's too much water in the atmosphere.
And like when you like swim deep into the deep end, your ears hurt.
Did she just hear what I said?
No. She was talking. I'm relating. My ears hurt now. My ears hurt. I'm sorry.
I just said it though, that's what I was saying. So the vapor pressure exerted depends on the rate of evaporation per unit area. More evaporation obviously means greater pressure. So this one's important too. You can change vapor pressures depending on temperature. You know that water is going to evaporate. Maddie, can you grab the door for me? Thank you. You know that water will evaporate faster if it's hot out, right? And the water will evaporate slower if it's cold out. So vapor pressure changes depending on temperature. So it's not a constant number. It depends on the molecule, and it depends on the temperature. And then the rate of evaporation and vapor pressure are higher in substances that have weaker intermolecular forces, which is what I just showed you here. All right, vapor pressure and equilibrium. I have a great example that today at lunch, I just was sitting there with Mr. Soap. I was like, vapor pressure and equilibrium. It's occurring right now. So I didn't have this for block 2, but what do you see inside my closed system? Condensation, which is what this is, but this is just such a better example. So I poured boiling hot water in here to brew my tea today. And then as that happens, right, the water molecules are going into the vapor phase. But because this is a closed system, and in a sense it really is, you can literally see that it begins to make water droplets because I've exerted enough of the vapor pressure in the system where it reaches its maximum point. So equilibrium is basically when the system is balanced. We'll do a whole section on equilibrium. But for right now, in general terms, equilibrium means like the system is at a standstill and it's balanced. It's not going to go one way or the other. It continually goes in a repetitive pattern, and everything is balanced on both sides. Not equal, just balanced. So in this picture, the gas particles go into the vapor phase, but then when this reaches its max vapor pressure inside the closed system, it turns it back into a liquid. And then the liquid goes into the gas, and then the gas goes into the liquid. This is like a cloud, right? When the cloud fills up with too much water vapor, droplets begin to form. Those water molecules begin to have attractive forces. They get too heavy to stay in the vapor phase, and then they liquefy. Well, this is what's happening in here. My gas particles started having intermolecular forces of attraction. They get too heavy, and then begin to liquefy all on the insides of the container. So you go from gas to liquid in equilibrium. And this is assuming that the temperature stays the same. It would stay in equilibrium. That statement there about shifting in the endothermic direction, you do not need to know that. All right, boiling points. This lecture is full of interesting information. We're going to talk about now how things boil. And you probably know some of it, but I'll relate all the chemistry now. So a liquid boils when its vapor pressure is equal to its atmospheric pressure. So right now, atmospheric pressure is pushing on us. It also would be pushing on a pot of water. So you go home today and you make yourself a pot of spaghetti. So you turn the water on, you put your spaghetti in when the water starts boiling. The water will not boil until the vapor pressure of the water is equal to the pressure from the atmosphere. So literally, atmospheric pressure is pushing down, and then pushing up is your vapor pressure of your water. These little particles, the bubbles that you see, well, first let's talk about the first bubbles that you see. What are the first bubbles that you see? Does anybody know? Yeah, the little ones that are on the bottom. Not the boiling.
Like trapped like air pockets.
So what's in air?
Like
What is in air?
orange.
Mostly oxygen and mostly nitrogen gas and oxygen, right? So if we have N2 and O2, that's already dissolved in our water. That dissolves in water because the vapor pressure of the atmospheric pressure pushes whatever it wants into your liquid. So if you're in like a really polluted area, it's possible that it's going to push pollutants into your water. And so we have mostly nitrogen and oxygen in that pot of water. So when you begin to heat it up, these compared to water, which one's going to boil first? These two. You're technically boiling out your nitrogen and oxygen first because these are only London dispersion forces, right? And then you're going to boil out your water, which is hydrogen bonds and London dispersion. So initially, all that you see are little bubbles floating up to the top, and that's your oxygen and nitrogen. Then you'll start seeing your water boiling. When your water boils, these are not air pockets. That's what people sometimes say, is that it's air coming out. It's not. What's happening is the water molecules are going from the liquid to gas phase. In this moment, they're going to a liquid to a gas, and they're trapped inside the water. And as they head up, more water escapes into the gas phase. So your bubble might start really small, and then it gets bigger and bigger and bigger and bigger, and then all of a sudden, bloop, and all the gas gets released. So all the water vapor goes into the atmosphere as these begin to boil out, right? So this is not air, this is literally water vapor. The little ones initially are the oxygen and nitrogen. So it will boil at a temperature that's equal to the atmospheric pressure. So let's look at what happens when atmospheric pressure changes. So if you've baked a box of brownies, or any box that's baked, you may have seen this at some point. Does anybody see on the back of the box that it says, if you're at high elevations, your oven temperature must be 400 degrees. If you're at low elevations, it should be 325. Anybody see that? Yeah, someone should get a box and bring it in when you see it. But look at the box next time. It'll give you cooking instructions for high elevations or low elevations. The reason this is true is because we take our pot of boiling water, so we're making spaghetti, and we go on the top of Mount Everest. We are never going to eat spaghetti. It's never going to cook. It doesn't matter how long you sit at the top of that mountain boiling your water, it's never going to cook. So the water will boil, you'll see boiling water, but your spaghetti is going to still remain hard. And so the reason why that's true is because cooking temperatures for food have a minimum temperature, right? Like you wouldn't be able to eat trying to give you an example. Like if you want to order a hamburger out, you can order it rare, medium, well done, right? Those have specific cooking temperatures, don't they, in order to get your food the way you want it. Well, spaghetti has a specific cooking temperature, and it's at roughly probably 100 degrees, the same of water that boils for us at our elevation. But if we go to the top of Mount Everest, the water will boil, but the temperature will not be hot enough in order to cook the spaghetti. You following? So you still have to maintain the proper cooking temperature, but this would not be the correct temperature. Why does water boil at 70 degrees C there? Because everything, all liquids boil, or water will boil, at atmospheric pressure. And when you're at the top of Mount Everest, atmospheric pressure is high or low? Low. What do we say when we go really high up? There's a phrase. Like, we would probably tease JC about what?
How's the weather up there?
Which is, sometimes people are like, how's the air? Is the air thin up there? Have you heard that phrase, thin air? Is the air thin? What does thin air mean? Low pressure. Because think about it. Molecules are literally small and large, right? There's small molecules, there's large molecules. So as you get higher up, heavy molecules just naturally sit lower, right? They can't really float around up high. So when you're up high, the atmospheric pressure is very low because there's not a lot of molecules up there. So if the atmospheric pressure is low, then water will boil at a lower temperature because you have to, in order for things to boil, boiling temperature has to be equal to the atmospheric pressure. You following all that? So the water temperature boils much lower, but your food doesn't get cooked. So what did they invent for people like this? Anybody know? No, to cook your food faster. You have it at home, I'm sure. No. A pressure cooker. A pressure cooker or a rice cooker.
Oh, rice cooker.
Why do we call it a rice cooker? It's just because it's pressurized. A pressure cooker. So, yeah, not like a crock pot. Crock pots can't pressurize. So if you have a crock pot, they usually have some area on it that will allow pressure to come out. I mean, there's usually a little hole on a crock pot to allow pressure to come out. Obviously, if you pressurize any sort of system and you keep it in a sealed container, what's going to happen? It's going to explode. So pressure cookers increase the pressure of the system, and then what does that allow to happen inside a pressure cooker?
There's more pressure, so the boiling point rises.
Yes. Are you guys listening? These are questions that you're going to have to be able to answer. If I use a pressure cooker, I am increasing the atmospheric pressure inside that system. And if I increase the atmospheric pressure inside my closed system, then I'm forcing that system to boil the water faster. So I can pressurize food in my kitchen and make it cook a lot faster. Do you ever see those infomercials?
No.
They're like, cook your food faster. And that's how they do it. They just pressurize it. All right, boiling points of different liquids. Just a few more slides and then we'll try some practice problems. The vapor pressure on the surface of a liquid depends on the strength of its intermolecular forces. A molecule restrained by strong intermolecular forces requires more energy to break free from its liquid state. When a system requires more energy to cause its molecules to enter the gas phase, it will also require more energy to cause its vapor pressure to equal the atmospheric pressure. So sort of thinking about this in terms of the amount of energy that would cause it to go into the gas phase. Last two, I think. Oh no, there's this one. All right, so let's make sense of these boiling points. So argon definitely exists as a gas at room temperature. Its boiling point is negative 186 degrees C. Only London dispersion forces exist on that. CH4, only London dispersion forces exist on that, but my boiling point is actually higher. Anybody have a reason why? So remember I said sometimes you will look at this, you will look at data, and you'll say, well, that's wrong, that must be a typo, but it's not, you just have to justify it. So why would you think that that's wrong? Because it has more electrons. Argon, if you look at the periodic table, has 18, and And if I look at CH4, how many does that have? 10. So according to polarizability, this doesn't fit my mold. But what could be a reason, because it's true, what could be a reason that the boiling point is lower?
Argon is a noble gas.
Clearly, the forces of attraction, the London dispersion forces, are stronger in CH4, even though it's not more electrons.
Argon is a noble gas, so it doesn't really care about bonding or anything.
Well, we can't say that it cares about anything. So, what about a noble gas, though?
It's not really attractive.
It doesn't bond, right? So we think of argon, here it is with its 18 electrons, but if I think of CH4, it has a larger structure. Even though it has less electrons, it has a larger structure. And so it does become more polarizable because there's more ability for it to push its electrons around that molecule. So being the fact that argon's so small, it has weaker London dispersion forces than CH4 because it's a larger geometry. Those are things that you would not have to know, but you would have to be able to justify it. So because you saw it, the only way you could justify it is to say CH4 must have stronger London dispersion forces and likely due to its structure being larger than just a single argon atom. C6H6 is benzene. That has only London dispersion forces, but again, that's much larger. And then water boils 100 degrees, and that has hydrogen bonds and London dispersion forces. Sublimation, what is that?
It goes from a solid to a gas.
Solid to gas directly, right? So the most common example of this is dry ice. So sublimation is a solid to a gas directly. And so CO2 is dry ice. This has very weak London dispersion forces. So it has the ability to go directly into the gas phase. So the first thing you would do is you would have to solidify it, which we know carbon dioxide does not exist as a solid at room temperature, right? So they pressurize this. They create a pressurized system in order to create a solid of CO2. So as soon as you put it into room temperature, it immediately goes to the gas phase because it has such weak intermolecular forces. So what you end up having is your delta H of sublimation is equal to the delta H of fusion plus the delta H of vaporization. Because this is your solid to liquid, and this is your liquid to gas. To go from a solid to a gas must be equal to the amounts of energy for both of these. Agreed?
Yeah.
So total energy has to be equal to fusion and vaporization. So this must have weak intermolecular forces, which it does, in order to get it to go directly from the solid to the gas phase. Solids with high vapor pressures have relatively weak intermolecular forces. So this is just basically evaporation, going directly into the gas phase. And then the vapor pressures of ionic solids clearly is very, very low. Because solids, ionic solids, like I just explained before, sodium chloride, they don't want to evaporate, right? They're intermolecular forces. They're not intermolecular. Their forces of attraction between cations and anions are too strong, and they have very, very low vapor pressures. So I think I will stop there.